For decades, the Strait of Messina Bridge was only a dream for Italian engineers that is turning into reality in just 6 years. To achieve this challenging feat of engineering, the bridge has to span 3.3 kilometers across the strait, making it the world's longest bridge. Featuring a unique deck design that is able to withstand winds that could reach up to 300 kilometers an hour, and a foundation that is able to sustain earthquakes of 7.5 in magnitude. So how is this even possible? The Messina Strait is part of the Mediterranean Sea, separating the island of Sicily from mainland Italy. The bridge is planned at the narrowest part of the strait, connecting Sicily with Calabria, and is approximately 3 kilometers in length. The location presents many difficulties, not only due to the large distance, but also the strait is an active tectonic area that is directly affected by the interaction between the African and the European continental plates. In addition, the strait is subject to strong currents and deep seabed, which makes it difficult to construct anything on water. Therefore, the two towers of the bridge were constructed on the land to give the bridge a strong footing, which will make the bridge officially the longest single-span suspension bridge in the world, beating the current holder, the 1915 Çanakkale Bridge in Turkey, with a length of 2,023 meters. The Strait of Messina Bridge will be 1.5 times longer than the current longest bridge. Choosing a single-span bridge means that the bridge must be able to sustain huge wind forces on the whole structure and withstand large seismic activities. This is why the two towers of the bridge have massive concrete foundations. The towers rise to a height of 382 meters. For height comparison, the towers will be as tall as the Empire State Building. The towers are made of prefabricated steel sections for easy construction, connected by 3 crossbeams, with the shape optimized for better aerodynamic performance. The towers will give the bridge a strong footing and will sustain large seismic activities of 7.5 in magnitude, which is higher than the highest recorded earthquake in the area that happened in 1908 with a magnitude of 7.1. The bridge's main span interact with the soil through the towers and anchor blocks. The towers will be able to sustain enormous vertical loads transferred from the main cables that carry the deck. The anchors will be able to support the horizontal loads of the bridge through the cables. The strong tension forces in the cables will allow the bridge to span large distances. The suspension system consists of 2 pairs of main cables, set at 52 meters apart. Each cable is 1.24 meters in diameter and made up of 349 strand cables. Each strand has 127 wires in it. So in total, each cable has 44,352 wires in it, which will be able to support the entire weight of the deck. From anchor to anchor, the total length of each cable will be 5,300 meters. The suspension bridge deck is connected to the cables through a series of vertical hangers. Let's have a look at how this creative design combats wind loads that can reach up to 300 kilometers an hour. The deck consists of 3 box girders. The 2 outer boxes are for roads, while the central box is for trains. The road platform has 2 lanes for vehicles, plus an emergency lane for each direction. The central box carries 2 railway tracks plus an inspection walkway. The bridge also has inspection and maintenance lanes located externally at each side of the road boxes, bringing the total width of the deck to 61 meters. Moreover, the deck structure is equipped with 4 inspection hatches inside the boxes, 2 in the central span and 1 in each of the side spans, which will help make these boxes future-proof and allow for easy inspection. The boxes are connected by 4-meter transverse girders spanning between the hangers, spaced at 30 meters. This brings the entire length of one deck section to 60 meters, which will be prefabricated and lifted to its final place. One of the big challenges in designing and building long suspension bridges is aeroelastic instability, which is the interaction between airflow and a structure. The main issue with suspension bridges is their flexibility, which makes them susceptible to wind effects, which could cause instability or excessive vibration. The best way to explain this phenomenon is to replace this deck with a continuous deck, to see how wind interact with both situations. When wind is blowing at high speed, the structure will interact with the wind, which can create uplift forces that lead to undesirable and often dangerous oscillations in the form of torsional and lateral vibrations, which can be very destructive if not properly controlled or damped. To combat this, Italian engineers came up with an aerodynamically designed, highly stable bridge deck. The deck section is composed of multiple airfoil shade boxes, which offer a highly reduced wind resistance. The open gaps between the boxes redirect the wind, which eliminates the lift forces. To improve wind serviceability further, the bridge deck is equipped with small airfoils to control the flow and act as aerodynamic dampers. The wind protection screens consist of perforated metal sheets tuned to reduce airflow and protect vehicles from direct actions of strong winds. And if you think this is enough to counteract the enormous wind and seismic forces in the strait, well, it is not enough. To damp the movements of the main span, the deck structure is restrained laterally at the towers by a large pendulum truss with X bracing. This creates extremely stable deck by smoothing the movements from the wind. While to counteract the huge seismic actions in the region, the deck is equipped with two pairs of hydraulic devices or buffers connected to short extensions of the transverse gross girders. The device behaves as a passive energy dissipating system for earthquakes. The span's aerodynamic stability is guaranteed for wind up to 300 km an hour, while the bridge will be accessible for traffic with wind up to 150 km an hour. The deck is expected to support 6,000 vehicles per hour and 200 trains per day. Moreover, the bridge will have a clearance of 74 meters in normal operating conditions and a clearance of 65.5 meters if subject to maximum loading. Therefore, it won't affect the maritime traffic crossing the strait. If building a bridge over the Messina Strait is that challenging, then why did Italian engineers choose to build a suspension bridge instead of a tunnel? Well, before landing on this bridge design, several feasibility studies were explored since the 80s. There were many concept designs for the crossing, and underground tunnels, floating tunnels, immersed tunnel tubes, and bridges, both single-span and multi-span. The issue with tunnels is that the strait is 72 meters deep and subject to strong currents, which makes the robustness and performance of the single-span bridge far superior to the tunnels and the two-span option, which can overcome greater distances without the need to build on water. Furthermore, it is more cost efficient and requires less material and usually built without the use of falsework. Therefore, the single-span suspension bridge was the best option overall. The cost is not fully confirmed. It was estimated to be 12.7 billion. However, this might not be the most accurate figure. This includes the upgrade of the road and rail networks in Sicily and Calabria, and includes the bridge, which is estimated to cost 5 billion or 40% of the total infrastructure network. The project is expected to boost the national GDP and involves about 300 local supplies. More than 100,000 people will be potentially employed. Most of them will come from the southern part of the nation, where the unemployment rate is high. A colossal infrastructure as the Messina Strait has never been constructed before, and the uncertainties related to the construction are one of the main reasons it hasn't been built yet. In addition to the technical challenges related to building the bridge, there are many other issues that always got in the way of building the bridge since the 80s. Issues such as government funding and doubt about the bridge's profitability and potential to improve Italy's southern region. There are also fears about the mafia influences in the region, which could affect the construction of the bridge. Although it is not the main focus of this video, it is worth pointing them out. Sometimes these challenges are more difficult to overcome than the technical challenges of designing and constructing the bridge. But despite everything, it will be interesting to finally see this project come to reality. Construction is expected to start later this year, and it will take 6 years to complete. The lessons learned from building this colossal bridge will be useful in pushing the envelope of how long future bridges will be. If you made it this far, then you most likely enjoy this type of content. To stay updated, consider subscribing for future engineering videos. That is all for now. See you in the next one. Cheers!